The cosmos constantly ships fragments of itself across space. Most of it hits Earth as a harmless rain of invisible debris, sleeting through our atmosphere undetected. But every now and then, the universe fires a high-energy subatomic projectile. On the night of May 27, 2021, one of those projectiles struck the upper atmosphere over the high desert of western Utah. It exploded into an air shower of secondary fragments, raining across a massive grid of surface detectors. To catch something this incredibly rare, you have to spread your net wide. The telescope array relies on hundreds of these isolated water tanks, spaced kilometers apart across the desert, waiting to pick up the precise timing of those secondary particles hitting the ground. When researchers in Tokyo reconstructed the Utah event, they calculated the original particle carried 244 exa-electron volts of energy. To put that abstract number into human terms, this single particle carried roughly the kinetic energy of a baseball thrown at 95 kilometers an hour, except all that physical momentum was compressed into a space smaller than an atom. Compare that to humanity's absolute technological limit. Buried under the Swiss-French border, the Large Hadron Collider is our most powerful machine, pushing protons to 13 tera-electron volts. The Utah particle carried roughly 20 million times that much energy. A single subatomic bullet walked into our atmosphere packing far more punch than our most ambitious engineering projects can generate. The universe is operating a particle gun we cannot locate. The physicists' logical next step was taking the arrival angle recorded in the desert and mathematically rewinding the trajectory to see where the particle came from. However, extreme particles face a hard physical space travel constraint known as the GZK cutoff. Space is filled with background radiation. An ultra-high energy proton slamming into these photons bleeds energy. This friction creates a strict mathematical ceiling. It cannot survive a journey beyond 300 million light-years. Its launch pad must be local. Because the GZK limit restricts the launch pad to our cosmic front porch, whatever fired this proton should be an obvious, massive astronomical structure blazing with radiation. Tracking the precise origin point is complex because charged particles do not fly in straight lines. They are constantly bent and redirected by the invisible magnetic fields threading through galaxies. To find the source, physicists run the flight path backward through complex models of the Milky Way's magnetic fields, mathematically untangling the bends until the trajectory is pulled tight into a straight vector pointing out into deep space. Most extreme cosmic rays tracked by observatories point back to known, highly visible cosmic structures capable of enormous violence. Active galactic nuclei, like Centaurus A, are exactly what we expect to find. These are galaxies harboring supermassive black holes that blast immense jets of plasma across millions of light-years, acting as giant natural accelerators. But when they traced the Utah particle's path, the line completely bypassed every known active galaxy, cluster, and black hole in our neighborhood. The trajectory pointed directly into what astronomers call the local void. It is a yawning bubble of empty space, containing no obvious matter, no X-ray flickers, and no gamma-ray glows. The particle, which they eventually named Amaterasu, came from a completely silent region, where by every known law of physics, nothing capable of firing it exists. This single particle unsettles the scientific community, because every possible explanation for its existence requires us to admit a major flaw in how we understand the cosmos. The gentlest theory suggests our current maps of the universe's magnetic fields are simply wrong, and Amaterasu's path bent far more drastically than our models can account for. Another possibility is that the reconstruction was confused because Amaterasu was not a proton. If it were a heavier iron nucleus, it would interact differently with magnetic fields, sending our reverse engineering off course. A third theory points to an entirely unknown class of dark accelerator operating invisibly in the deep cosmos. The most extreme theory argues that we are witnessing the decay of a super-heavy dark matter particle left over from the Big Bang, finally detonating and releasing a sliver of its hidden mass. If true, this means the stretches of space we consider empty are actually filled with unimaginably violent engines performing invisible work. Every minute, fragments from these unknown engines sleep through our atmosphere and our bodies. We live our lives inside the active firing range of the deep cosmos. The Amaterasu particle is a postcard with no return address. It proves the cosmic geography is stranger than our models allow, leaving humanity watching the desert, waiting for the darkness to flash again.